All right, if you can hear that noise in the background, that is the gas company digging up my street, and for that I apologize. All right, so we have a brand new unit, and in this unit we're going to be doing our focus on summations turning into integrals. So we're making a big switch from derivative calculus to integral calculus, and today's video is actually not officially in this checklist because it's just a review of some pre-calculus knowledge to make sure that you are ready to work on our first big calculus topic for this unit, which would be limit summations. So we're going to start, oh no, all of my answers are there. Okay, I erased them. Those were left over from last year. We're going to start by reviewing our sigma notation. So this is our symbol sigma, and when we see sigma, it means that we are supposed to do a bunch of adding. So we call this summation notation. All right, so we're going to focus on summation notation. We're going to break down each one of these parts. So when we think about this, I represents our index. This will be the thing that varies. So it's our variable, if you will. This number here is going to be our start value. So we're going to start, in this case, when I is equal to 1. This up here is going to be our end value, or our terminal value. This will be when we stop. And then the part on the inside, this is what we would call our expression. So this will be the thing that has the variable in it. This will be what varies. And then in between each one of those things that changes, we will be adding because of the sigma. All right, so evaluate the following. Remember, evaluate means that we're going to be finding a value. So thinking about this first one, it says sum all of the numbers of I, starting with 1 and ending with 6. So I'm going to add 1 plus 2 plus 3 plus 4 plus 5 plus 6. So I stop when I is equal to 6. You might want your calculator out, but also we can say 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to 21. So this summation is equal to 21. That's its value. A little cheap shortcut for how you could get there is 1 plus 6 is 7, 2 plus 5 is 7, and 3 plus 4 is 7. And you've got 3 of those pairs, so 21 is your sum, 3 times 7. If you want to know more about this process, you can look up information about a mathematician by the name of Gauss. And there's a story from when he was around 10 years old and how he came up with a formula for that, all on his own. The things you can do. Wasn't even a pandemic going on. All right, this next one, we are summing. Our index this time is j. So we're going to start when j equals 3. We're going to stop when j equals 7. So this will be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. Typing all of that into your calculator, we're going to end up with 135. So again, this full statement is telling us what to do. It says sum up the numbers from 3 to 7 of the square of each of those numbers, right? That's the j squared. This next set of directions is a little bit different. It says write an expression or a formula to represent this summation. Well, this is different because, first of all, k is our index, so that's something new to us. We're going to start at 1, but we don't know where to end. Weird. Well, the first thing I can do is I can factor out anything that is not dependent on k, right? If we think about this as an expression, some sort of a function, anything that doesn't depend on k can be factored out in front. So what this really means is I'm going to take 1 over n, and then my first number is going to be 1 squared plus 1, plus 2 squared plus 1, plus 3 squared plus 1. Where does the madness end? It ends when I get to a number n squared plus 1. So I've left this big blank space here. If I'm starting at 1, 2, 3, 4, 5, 6, 7, 8, whatever it might be, and I'm supposed to end at n, how would I indicate the number 1 before n? Well, that would be n, but 1 before it. So in this middle part, I would have had n minus 2 squared, n minus 3 squared, n minus 4 squared. So it's pushing these two things together, and we write this ellipse in the middle to say we're going to keep doing this, right? Starting at 1 and ending at n. So this is some sort of an expression or a formula. This is not a value, right? Because there's no value that you are getting out of here. We did not evaluate that. Okay, so summation formula is with a double star, and that double star at the bottom of your page says, yes, you are responsible for these. So if I am summing up an index of 1 to n of a constant, right? So c is not dependent on that index I. Well, that's going to be whatever that c value is times n. That's a shortcut. Our proof of that is really what I'm doing is it says take c plus c plus c plus c plus c. Well, how many c's do I have? I have n c's. Okay, so we'll use that formula here in just a little bit. This one, if I have a linear function, so my index is I, and I have I to the first power. So we've got a linear summation. This shortcut formula, instead of listing them all out, is going to be n times n plus 1 all over 2. And this is where a proof of this gets interesting. This is kind of like how on the first one, I was summing from 1 to 6, and I ended up with 21, which was 3 times 7. Well, looking at this, 6 divided by 2 is 3, 6 plus 1 is 7, 3 times 7. This again is often referred to as Gauss's formula, which is the shortcut for adding the n's, thus using n in our formula. But let's talk about why this is. So I'm going to say that the sum, s, starting at 1 and going to n, would be 1 plus 2 plus 3 plus n minus 2 plus n minus 1 plus n. That's one way of writing my sum. Well, then another way of writing my sum would be to count backwards. Count n plus the number before it plus the number before that one plus 3 plus 2 ending at 1. Thinking about this as one giant addition problem, if I add these two things together, I get 2s. If I add these together, I get n plus 1. If I add these together, I get another n plus 1. If I add these together, n plus 3 minus 2 is again n plus 1 plus, you got it, n plus 1 and another n plus 1, finally ending with, I'm running out of colors, with another n plus 1. All right, well, how many n plus 1s do I have? 1, 2, 3, dot, dot, dot. I have n number of n plus 1s is equal to twice the sum, which means that the sum I'm looking for is equal to n plus 1 divided by 2. Now, are you responsible for that formula? Yes. Are you responsible for being able to reprove it? No, but it's kind of a cool proof when you think about it. All right. The next ones we won't prove in here. You can look up videos online for how to prove them if you are curious. This one starts the same as what we just saw, n plus 1. But then we're going to multiply by 2n plus 1, and this one's going to divide by 6. Another way to view this would be to actually distribute out the top. So 2n to the third plus 3n squared plus n all over 6. So these two things are equivalent if you're ever summing a quadratic. So when you have your index squared. This one then when you have your index cubed, n squared times n plus 1 squared all over 4. This is actually Gauss's formula, but just squared, Okay, and again, there's proofs of this online that you can look at. The constant multiple rule. We've learned this one before. Because my index is I, this term has an I in it, so we're dependent on that, which means the K, the constant, can be taken out in front. Just like when we've taken derivatives, right? We can pull the K out and just kind of forget about it. The last thing then is, it is always okay to sum sums. So if I'm summing x plus y, that's the same as summing all of my x's and summing all of my y's. So again, you are responsible for these formulas. So start using them, start learning them. We'll use them often enough that you should get used to them. All right, so you have 6 problems to try. I would go in order 1, 2, 3, 4, 5, 6. Something to note, numbers like 4, 5, and 6 are what I was getting at before, where you can break this up and you can take the sum of I squared plus the sum of I plus the sum of 3, right? So you can break that up into a sum of sums. Go ahead and pause your video. See if you can use your formulas to solve for each one of these. Pause your video, try them for yourself. You might want your calculator. All of these will come out with a numerical value except for number 6. It's still going to have some sort of an expression in it. So pause your video, try them. All right, here's your answers. And in orange is each one of the formulas that I used. So in this case, I'm summing a constant. So C times N, 3 times 10. Summing a linear, Gauss's formula, n plus 1 over 2. Summing a quadratic, n plus 1, 2n plus 1 over 6. All right. Number 4, well, I'm just summing the 3 values that I just found. 385, 55, and 30. For question 5, again, summing the 3 values that I found, except I have a 2 that I can drag to the outside as a constant multiple. So it's 2 times what I found just above. And then this last one, very similar concept, except 1 over n is my constant. Even though n is something that varies, it's not the official variable of this expression, which is I. So I can take out the 1 over n, and now I still just have I squared plus I plus 3, which was my 470 from number 4. Finally, just showing this in one more way, if I had started with 1 over x, right, this would be 1 over x times 470. Just like when I had 2 times all of that, it was 2 times 470. So this number is still considered a constant multiple because the variable x is not the same that the index is saying is supposed to vary. All right, so that's it. That should be a review for you from pre-calculus. There are some homework problems in your textbook. Make sure you look over those and try each one of them. You should be using your formulas. So you are responsible for constant, linear, quadratic, cubic, and constant multiple. Also remembering that you can always sum some sums. All right, that's it.